Okay, so this is the review for test 2. So you should have the key already, but this would just be for your viewing purposes if you needed to look to see how I got an answer that was on the key. All right, so let's get going. I'm just going to use the actual review itself for the first one. So notice I said use the given graph below and a table to show y equals 5 to the x. In other words, I want you to graph that. So what I mean by a table is you can always set up an XY table / chart and pick some X's and plug them in to find your Y's. Okay, so always how you find things in this column is you plug in your X's. Okay, so I'm going to start with 0, 1, and 2 first because those are kind of easier. So 5 to the 0 power is 1. Remember, anything to the 0 power is just 1. 5 to the first is 5. 5 squared is 25. So notice the values are getting very large very sharply. So let's go ahead and graph those. So 0, 1, 1, 5, and then 2, 25 I'm not even going to bother with, but that does tell me that, hey, my graph is going up very sharply in that direction. Okay, and then remember these are negative exponents, so this would be the same as 1 over 5 to the first, which would just be 1/5, a very small number, right? This would be the same as 1 over 5 squared, which would be 1 over 25. So the values basically are approaching the x-axis. Actually, the x-axis is what we call an asymptote. Okay, it's getting super, super close to that without actually crossing it. Okay. All right, so we're going to use this graph and we're going to kind of compare what's going on with these graphs, right? So the first thing is notice that I changed the base, right? I changed it to 8. So I'm going to move over here. So I'm just going to say there was a graph there, right? We did that off to the side. So I want to compare the graph of y equals 8 to the x power. Make sure you don't write 8x, it's 8 to the x power, okay? And notice the only thing that will really happen with this compared to the graph we just did is that because the base is bigger, the graph will be steeper. So remember that the bigger the base, the steeper the graph. Okay. So let's look at B. So y equals 5 to the negative x plus 2. Okay, this is actually some review from Unit 1, honestly. Okay, it's just using this new graph. So notice the parent function would be y equals 5 to the x, right? And this would be a shift up 2 units. And then this negative sign, notice it's not in the front of the equation. It is on the inside. So this would be a reflection over the y-axis. And since there are 2 changes here, I'm going to number them here. Remember, we always reflect before we shift up or down. Think of it like you work from the inside out, remember? So this is on the outside, so it's the shift or change that happens last. And then last but not least for this one, y equals negative 5 to the x plus 3 power. Okay, so notice this time the negative sign is to the front of the function, so this would be a reflection over the x-axis. Okay, when it's inside, it's a y-axis reflection. When it's to the front, it is a x-axis reflection. And then notice the plus 3 is not at the end, right? It's inside the function. So this is going to be a shift left 3 units. So I'm going to underline that. Remember, horizontal shifting works the opposite of the direction of the sign. So even though it's a plus 3, it would actually be a shift to the left. And if you work from the inside out, this one actually comes first, followed by this one. Okay. Okay, so let's look at number 3. 10 to the 2x minus 1 power equals 10 to the x plus 3 power. Okay, so notice that here the bases are the same. So if you can get the bases the same, or if they already are, if the bases are the same, then we can set the exponents equal to each other. You cannot do this if the bases are not the same, but notice here they are. So pretty easy. We don't really get rid of the 10, we just don't really care about it. So we're going to set the 2 exponents equal to each other, and then it's just a basic couple step algebra problem that I can do, right? So I would subtract x from both sides. I would add 1 to the other side, and it looks like I will get x equals 4. Okay, and note, you could check this on your calculator, right? You could plug in 4 to this original equation. So you could say 10 to the 2 times 4 minus 1 power, get that answer, and then do 10 to the 4 plus 3 power, and you should get the same thing on both sides. Okay, so remember, on a lot of these, you can actually check it on your calculator, and I hope that you will. All right, so what about this one? Okay, so note the bases are the same here too. So we're going to set x squared equal to 2x plus 3, okay? And then we'll just ignore the 7s and solve that. So I've got x squared equals 2x plus 3. Remember, anytime you have a squared equation, I want to solve for 0. So I'm going to move these terms over. Whatever I do to one side, I have to do to the other. So I get x squared minus 2x minus 3 equals 0. So I would either AC method, or if it didn't factor for some reason, I would use quadratic formula. This one does factor, and I don't even honestly think I need AC method, since remember that number in front of x squared is 1. So the numbers that multiply to give us -3, but add to give us -2 are -3 and 1. And then you would just set each thing equal to 0. So it looks like we get 2 answers we could check, right? X equals 3. And also x could be -1. Okay. All right, so let's look at number 5. So notice number 5 looks kind of similar to number 3 and 4, but notice the bases are not the same right now, so you are not allowed to set the exponents equal to each other. Notice this one is an understood exponent of 1, right? So we want to rewrite this as a base of 2. So our first method in solving problems like this, if we can get the bases the same, is to do so. So we're going to leave the left side the same, and then we're going to think, how many powers of 2, or how many exponents do I need to multiply together to give me 16, right? So 2 times 2 is 4, times 2 again would be 8, sorry, and then times a fourth 2 would be 16, so it's actually 2 to the 4th. Okay, so notice now we have what we didn't have before, right? Notice that now that we worked a little bit, the bases are the same. So I would set 2x plus 4 equal to 4, or sorry, 2x plus 1 equal to 4, and solve from there. So I'm going to finish it on here. So I've got 2x plus 1 equals 4. If I subtract 1 from both sides, I get 2x equals 3. And then divide both sides by 2, so x is 3/2. Okay, and again, that could be checked on your graphing calculator also, or on your scientific calculator, whatever kind of calculator you have. So make sure that you check those. All right, number 6. So 10x e to the x minus 5 e to the x equals 0. Now I know this looks messy, but our goal, anytime we have an equation equal to 0, no matter how ugly it is, our goal is to try to see if we can factor it. In other words, try to see if we have any common terms we could take out. So notice they both have a 5 in them, and they both have that e term. So I'm going to factor 5 times e to the x out here, and then I will get 2x minus 1. Like if I divide a 5 e to the x term out of here, I only get 2x left. If I divide a 5 e to the x out of here, I just have a 1, since something divided by itself is just 1. And then you set each part equal to 0. Okay, so you set 5 e to the x equal to 0. And you set 2x minus 1 equal to 0. Okay, but just so you know, this can never be 0. Okay, nothing to a power can ever be 0, because even if you raise it to the 0 power, it's just 1, right? 5 to the 0 power, or e to the 0 power rather, not 5, would just be 1, not 0, so that's impossible. But here we do get a valid answer, right? We get x equals 1/2. Okay, so we don't get an answer from this part of the problem because it is impossible for anything raised to the x power even e to ever be 0, so we just ignore that part of the answer. Okay, it doesn't yield any results. Okay, so let's look at number 7. So we have an equation for the percentage of married families. Okay, notice that's an exponential function, right? Because we have a variable in the exponent spot. So you just really honestly just need to read the problem and kind of see what it's asking. So notice that T is in decades. And it's actually decades after 1970. Okay, that's just listed in the problem. So when it asks you to tell the percentage of families who were married households in 1970, 80, 90, and 2000, for 1970, it will be T equals 0. For 1980, it will be T equals 1. For 1990, it will be T equals 2, because notice this is 1 decade after 1970. This is 2 decades after 1970. And then finally, in 2000, it would be 3 decades after 1970. So we have a formula for percentage, so we'll just use the formula in our calculators. So for this one, we'll find P of 0. So take the equation you have above and plug in 0 for T. Okay, so this comes out to be, by the way, e to the 0 power is just 1, so this comes out to be 86.9%. So in 1970, 86.9% of households included a married couple. Okay, so P of 1 is going to be 86.9 e to the negative 0.05 times 1 power. Okay, and this works out to be approximately 82.7%. So in 1980, that fell to 82.6, or 0.7, I mean. If we plug in 2, you will get 78.6. So, you know, if you're using kind of common sense, right, I think we all know that probably the percentage of married households is dropping. Okay, if we pay attention to society at all, right? And so I don't really know why I started to open a parentheses there, but let's go ahead and get rid of that, if my whiteout will let me. All right, so because I haven't shown you the calculator for any of the previous ones, I want to show you the calculator for this one just to make sure. But your E button is usually on the left-hand column, so you would do 86.9 times e to the power of, and then notice my calculator opens up a exponent box, and then you would say negative 0.05 times 3. Okay, if you have an older calculator, you might need to put parentheses around the exponent since it has 2 pieces. But mine opens up an exponent box, so that's not super necessary that I do that. So in 2000, it had fallen again to about 74.8%. Okay. So that's all there is for that one. All right, so number 8 is when we start talking about logarithms in some way, shape, or form. Okay, so number 8 says to rewrite this true exponential statement, because by the way, 3 to the negative 2 power is 1 over 9, right? A negative exponent means rewrite it as a fraction, so it's the same as 1 over 3 squared, and 3 squared is 9. Okay, so this is what we would call exponential form. So all I'm asking you to do is rewrite it in exponential form, and basically you just need to know, or sorry, logarithmic form, you just need to know where things go. So it's always log, base, and then it's always whatever the base was over here. Okay, remember the answer to a logarithm is always the exponent, and then by default this has to go in this spot. Okay, so notice I kind of do it out of order. It's base to the exponent power equals this number right here. So you are definitely going to need to know how to kind of change things from one form to the next. So I don't know that I'll put a question just like this on the test, but there will certainly be some times where you have to switch formats and understand that the answer to a logarithm is always the exponent. So you might want to jot that down if you've forgotten that in some way. All right, so for number 9, I'm going to write off to the side there are 3 log rules. Okay, make sure you know them. They are the product rule, the quotient rule, and the power rule. Okay, so make sure that you know those, okay? And so that is the rules we're going to use for the next few questions. Okay, so the first thing is what we're allowed to do with these numbers in front is we're allowed to move them back to the exponent because of the power rule. So this would be the same as the log of a cubed plus the log of b squared. Okay, and this is due to the power rule. The power rule says you're allowed to move exponents to the front, or if they're in the front, you're allowed to move them back to the exponent spot. And then last but not least, and by the way, sometimes you'll see this. I usually include parentheses. It's not super necessary unless you have more than one part, which we're actually about to. So notice we're adding here. Okay, so the rule that allows you to combine with addition is the product rule. So this is going to be the log of a cubed b squared, okay, because again of the product rule. Notice this time you do need to make sure that you put parentheses to indicate that the a cubed and the b squared are both part of the log term. Okay, so you'll need to make sure that you do that when you write it out. All right, number 10, same kind of format. Notice this time we're using natural log. The rules that I wrote to the left here apply to any log at all, including natural log. Okay, so the first thing I would do is just what I did in number 9. I would notice that, hey, these numbers in the front could be rewritten as exponents. So this will be x to the 1/2 power. This will be the natural log of y cubed. And then don't change your signs, so it'll be minus the natural log of z to the 4th. Okay, so this is because of the power rule. And then notice we have two signs going on. Okay, we're adding the first time and then we're dividing, we're subtracting the second time. So we're actually going to use two different rules. So it's going to be the natural log of x to the 1/2 y cubed. But then because this is being subtracted, it means it's a negative exponent, so it goes to the bottom. Okay, so this is because of product and quotient rule, actually. Okay, but just know that honestly, the best rule of thumb is anything with a positive sign goes on top, and anything with a negative sign goes on bottom, because remember, logarithms are just fancy exponents anyway, and negative exponents do go on the bottom. So you could also, if you wanted to, change that square root or that x to the 1/2 power to the square root of x. That's a multiplication dot there. So I would basically take either of these formats. Okay. All right, so starting with number 11, we're going to start applying some of this log stuff. Okay, so can you solve things that use logs? Okay, so notice I don't tell you you have to rewrite this, but to understand what you're doing, you pretty much have to rewrite this. So you would rewrite this in exponential form because we're most comfortable with exponents, not necessarily with logarithms, right? So that would be the base raised to the answer power equals 81. Okay, and then that should be something we could answer, right? How many 3's does it take to get to 81? It takes 4. All right, so notice in these next few, I'm just kind of moving around the unknown quantity as we go. So if I asked you to solve this, again, we're not going to stick with this format. We're going to rewrite it. Okay, so we're going to rewrite it as x to the 3rd power, right, equals 216. Okay, so maybe you don't know this one right off the top of your head, but you could solve it, right? How do you get rid of a cubed if you want to know what x is? You cube root it. So you would cube root this side and this side, and then you could just use your calculator. So you'll end up getting x equals 6. Number 13, log base 2 of 2x plus 5 equals 3. So notice this is actually very similar to what you did in number 11. You just, again, need to rewrite this. So that kind of needs to be your go-to rule with exponents, or sorry, with logarithms. Try to rewrite it when you can. So if you rewrite it, it's 2 to the third power equals that 2x plus 5. But notice that's something we can do, right? 2 cubed is 8. Make sure you don't do 2 times 3. That's a common mistake, right? It's 2 to the third power, okay? Equals 2x plus 5. So we will subtract 5 from both sides. So we get 3 equals 2x. And then we will divide both sides by 2. So we get x equals 3 over 2. Okay, always make sure you make your answer clear, circle it. So notice I had needed this rewrite step to solve the problem, but in the end I would just want to know what x is. Okay, so that should be what you circle. All right, so when you look at 14 and 15, notice that the rewrite part would be a little more of a challenge because we have 2 logarithm terms. Okay, but lucky for us, we have some rules that might allow us to combine these, right? So we don't want 2 log terms. We would prefer to just have 1. So we're going to combine, and then you have to decide which rule to use, right? Notice that I'm subtracting here. So I'm going to combine using the quotient rule. So this is going to look like the log base 5, notice that doesn't change, of 2x plus 1 divided by x minus 2 equals 1. So now I just have something that can be rewritten. Now I can do my rewrite step because now I have a single logarithm. And the rewrite step again would be base to the answer power equals the other part. Okay, so notice this is really just like 5 over 1 equals 2x plus 1 over x minus 2. Okay, and when you see it like that, hopefully you see that you can actually cross multiply here, but that is how you have to solve this. So I'm going to move up over here. So basically we're going to do 5 times x minus 2, make sure you use parentheses, equals 1 times 2x plus 1. And then you would distributive property here. Notice you don't even need a distributive property there, right? You would get 5x minus 10 equals 2x plus 1. And then start to move terms around. So subtract 2x from this side, add 10 to this side. And you get 3x equals 11. Divide by 3, and you get x equals 11 over 3. Okay, so notice it was kind of similar to the ones we did before, but we had to combine them before we were allowed to do the rewrite step. So when you want to rewrite a logarithm, you actually need a single logarithm. So you might need to use one of your 3 logarithm rules in order to condense or combine them to 1. By the way, the log rules don't work at all if the bases aren't the same. Okay, so if the bases for some reason weren't the same, you wouldn't have been able to do any of those combination steps. So we are going to combine again, but notice this is going to be a different rule. So we're going to combine using product rule this time. So this is going to become the log base 2 of x times x minus 7. And then we're still equal to 3. Okay, so before I do the rewrite step, let's simplify this. Like, let's use distributive property there. So this is the log base 2 of x squared minus 7x equals 3. Okay, the parentheses would be necessary because it's, you know, got more than one piece. So now we are ready to rewrite this guy. Once you get it to a single simplified logarithm, you want to rewrite it right away. So it's 2 to the third power equals the other thing, which looks like x squared minus 7x. Okay, so this is 8. So we would subtract 8 from both sides. So we end up getting 0 equals x squared minus 7x minus 8. And then we just see if we can factor this. So the factors of negative 8 that add up to negative 7 would be minus 8 and plus 1. But also remember that there are certain numbers we are not allowed to take the log of. Okay, so this is actually our only legitimate answer. This one works out to be invalid because you cannot plug it back in to check it, right? You can't take the log of a negative number, okay? So you need to make sure you remember that rule, but you can't take the log of a negative number actually or 0. Okay, so anything that would require that you take the log of a negative number, we're going to ignore and just keep the other answer. Okay, remember that you don't always get rid of an answer. That is often what you do, but not always. Okay, so if, by the way, if both answers were valid, then the answer, you would have 2 answers. Okay, if both answers ended up being invalid, you would have a no solution situation. All right, so the next section, I ask you to use logarithms to solve. Now notice, I can't solve these like I did the ones before where I tried to get the bases the same, because the base is e. And remember, e is that number 2.718281828, so you're never going to be able to get the bases the same here. Okay, but what you can do is maybe use logarithms, and that's actually what the instructions for this section tell you anyway. So first you need to isolate the exponential term, in other words, the e thing. So this is what I get when I isolate it, right? And then remember, how do you undo an e? So I'm going to rewrite it just so I have room. You undo an e by taking the natural log of that e function, but whatever you do to one side, you have to do the same thing to the other. And the reason that is helpful is because the power rule allows us to move this to the front. Okay, so I'm going to write in here, this is because of the power rule of logarithms. And the ln of e is actually just 1. Okay, so this becomes just negative 2t. And then on the right, we still have the natural log of 6/5. So notice now we just have one more step and we actually have something we can plug in our calculator, right? We want to know what t is. And now that we have t out of the exponent, we can find that. So we end up getting, I'm going to write it over here, t equals the natural log of 6/5 and then divided by negative 2. Okay, so on the test, I would want to see how you came on that answer. Like, I want to see this exact answer, but then I'll probably tell you to give me the decimal in so many decimal places. So I don't know if I specified that on the review. It doesn't look like I did, but I do want you to be able to punch it in the calculator. So the natural log of 6/5 and then divided by negative 2. Okay, so let's say we're going to round it to 2 decimal places. So this is approximately negative 0.09. Okay, so I'm going to circle both of these because on the test I'm going to ask you for the exact answer, which is this, and then also what that comes out to be approximately as well there. Okay, so remember the power rule of logarithms allows us to get that exponent out of the, that variable out of the exponent spot. Okay, so we tend to use, or I tend to use at least ln a lot. Okay, you want to use ln when it's e, but when it's base 10, okay, you actually want to use the other log, and you actually can use either one no matter what. But in this case, you would want to use the common log, which is log log. So I'm going to take the log of both sides. I'm not multiplying by log. I'm taking the log of both sides. And again, why I do this is because the power rule of logs allows me to move this to the front. And then actually, the log base 10, or this is understood to be base 10 already. So just like ln and e get rid of each other, so do common log and 10. And so you end up getting t equals the log of 153. Okay, and notice, remember that when there's no base here, it's understood to be 10. The understood base for ln is e, and the understood base for log, when there's not a number there, is actually 10. So I would just do log of 153, and I would get right about, if I round it, 2.18. So again, on the test, I'm going to want to see both answers, both the exact answer, which is this, and the approximation, which is that. Okay, so we are going to use logarithms a little bit later in the review for the finance section, but this is the last one that just straight up uses logs or exponents. And then we'll move on to the finance unit. So here is an equation that describes the temperature of a cup of coffee T minutes after it's poured. Okay, so you might want to write this down, but T is the temp in Fahrenheit, and then T is the time in minutes. So this is in degrees Fahrenheit, okay, and that is the time in minutes. In other words, the coffee is going to be hot when it's poured, right, but as it sits, it's probably going to cool off. Okay, this is actually called Newton's law of cooling. Okay, has no reference to my last name, but that's what it's called. Okay. So the first question says, what was the temperature of the coffee? So let's stop right there. I'm trying to find T, right? Capital T, I should say. When the coffee was poured, right? So when it's poured, no time has passed. So it's asking what the coffee would be right off the bat, right? At time 0. So we're just going to use our calculator, or maybe not, because 7 plus 100 and then e to the negative 0.04464 times 0 power. Notice that this is just going to be e to the 0 power, and anything to the 0 power is just 1. So you can use your calculator if you like, but actually you don't really need it on this one. So this would be 70 plus 100, or 170 degrees Fahrenheit. Okay, if it would have asked for the temperature after 5 minutes, you would have used this formula and plugged in 5, okay, whatever it asks for. And then the last question on this one says, when will the coffee be 120 degrees Fahrenheit? So it's not asking you to find the temperature, it actually told you the temperature, right? So it's asking you to find little t when capital T is 120. Okay, so in other words, what it's asking you for is to plug in 120 for capital T, and then e to the 0.04464 t power. Okay, so this is very similar to question number 16, just with a little more complicated numbers involved, right? So if we want to know what t is, we first need to isolate this. We need to get this part by itself. So I'm going to work to do that. I'm going to subtract 70 from both sides, and that's going to give me 50 equals 100, and then that e term again. And then I would divide by 100, because again, I'm trying to get the e part all alone. So you can simplify this. 50 over 100 is just 1/2. Okay, you could also write 0.5, but don't change it to a decimal if it's not a pleasant one. And then you get to the e thing again. So then, how do you undo e? So I'm writing it again, although I'm really tired of writing that decimal. I'm writing it again so I have room to work, right? I need to take the natural log of both sides. I could take either type of logarithm, but with e, I always want to take the natural log. And the purpose of that, remember, is so that I can move this guy to the front because of power rule. So what I end up getting, and remember ln and e cancel each other out, so I get the natural log of 1/2 equals negative 0.04464 t, right? Because I got it out of the exponent spot so that I could actually mess with it. And then finally, we will just divide by the term we want to move over. Okay. So if you work that out in your calculator, it is approximately 15.53 minutes if we round to the nearest 2 decimal places. Okay, I don't think I really said what to round it to on the test. I will be specific about how many decimal places I want to round. But a good rule of thumb is to just always use 2 if you're not sure. Okay. Okay, so let's start with the finance section. So the biggest thing that I want you to realize is that in the finance section, you have to make sure that you know what formula to use. Okay, that's going to be different maybe from when you did your homework, right? When you did your homework, it was separated into sections, and you kind of knew what formulas went with that section. Okay, well on the test, it's not going to be that way. You're going to have to read the problem and understand what it's asking for. So notice on number 19, I actually tell you what formula to use, okay? You will be provided all of these formulas. So on number 19, I'm asking you to compare two accounts. So let's start with account A versus account B. Okay, so we know that, hopefully we know that the more often interest is compounded, the more money is earned, okay? So the problem is that we are getting a better interest rate for our savings account, which by the way, that's way too high for a real savings account, but account A offers us a better interest rate, but it only compounds it semi-annually, twice a year, as opposed to account B that has a little bit worse interest rate, but it compounds it more frequently. So the question is, does that make a difference or not? So remember the formula is 1 plus the rate written as a decimal, so this rate is 11.5, over the how many times a year are you compounding it, which is 2, and then raised to the same power minus 1. Okay, so use your calculator, but you get 11.83%. Okay, so I'm going to circle this. So what this means is that they can tell you your interest rate is 11.5 all day long, but your effective interest rate, or the one you're actually paying that has been adjusted for frequency of compounding, is actually 11.3%. Okay, so we'll use the same formula for this account, but remember we got to change the interest rate, right? The interest rate is 0.1125, and we're compounding monthly, which means the M is 12. Okay, and then we raise that to the 12 power minus 1. So notice we actually have to carry it out to 2 decimal places to really get a comparison, okay? And so because it's a savings account, we'll choose this one, right? It's just a little bit better. So I'm going to say choose account B. Just remember that if it would have been a credit card or something, right, you would have wanted to choose the least amount of interest, right? But because it's a savings account where you'll be gaining the interest, you would want the least amount, or sorry, the most amount of interest you could have. All right, so let's go on to question number 20. All right, so you have to be able to read through the problem, okay? Notice that this formula mentions simple interest. So we have 2 simple interest formulas, and you just need to pick the one that would be appropriate. It's asking for the amount at the end of the loan, and then it asks for interest, right? So we're going to first find out the amount at the end, right? You will be given these formulas, but you'll have to know how to use them. So when you see this formula, you need to know how to use it. Okay, so P is the principal, remember, A is the final amount, R is the rate, T is the time in years. So if we plug in what we know here, we get a $3,000 original investment, and then 1 plus the interest rate is 4.5%, so that's 0.045. Make sure you move the decimal place twice. Okay, and then it's 4 years and 8 months. So you can either figure this off to the side, or you have to be able to say, hey, that's 4 8/12, right? Because this quantity always has to be in years. Okay, so just make sure you can kind of figure that out. So I'm going to show you how to enter that in the calculator in a minute, but we could kind of clean this up if we wanted. This is 3,000 times 1 plus 0.045 times 4 2/3. Like that would reduce to 2/3. But notice I can't really change this to a decimal because it's actually 0.66666 repeating. Okay, so let me show you how you'd enter this in on the calculator. So you basically enter it in just like it is, 3,000 times 1 plus 0.045 times, and then how you enter in a mixed fraction like this is you say 4 2/3. Okay, so you say like 4 and an extra 2/3, and that's how you get what the correct answer is, which is $3,630. Make sure if it's money that you indicate that with a dollar sign. Okay, notice there are no cents involved here. And so then the last thing would be the interest. Now you could use the interest formula, or you could just use your common sense, right? If the amount in the account at the end is $3,630, and you only started with $3,000, then the difference between the two should be your interest. So you can use the interest formula, but I say you don't really need it. Okay, and so that's how you would get both parts on number 20. Notice that if it's simple interest, it's going to state that. Okay, so it will actually use the phrase simple interest. You're not going to have any cases where you have to try to figure out what it is that they mean. You will be able to figure it out by them telling you, hey, we want you to use simple interest here. Okay, so let's look at number 21. So if Joe makes $200 deposits at the end of each month in a money market account earning an interest rate of 6% per year compounded monthly, how much will he have in his account after 7 years, assuming he makes no withdrawals? Okay, so we have to figure out which formula to use, right? So notice we know the payment, so I'm going to kind of give you some pointers here. We know the payment. Okay, so that means we only have two options. Okay, we have two formulas that cover periodic payments, right? And it's either future value or present value, right? And so notice that it will include interest, so we're going to use the future value formula. Okay, in other words, when he deposits money, the amount will include interest, so that means it's future value. So that's kind of the telltale sign that tells you which formula to use. Remember, present value does not include interest yet. Okay, present value is before interest has been added. And this amount would definitely include interest because they're saving and they're getting interest along the way. Okay, so the formula is future value equals, remember it's payment times a bracket with a fraction, right? And what goes here, we worked these off to the side in class. So what goes here, the interest rate is going to be whatever the stated rate is divided by number of times per year that it's compounded. Okay, and then remember that N is actually number of payments, right? So we're doing 12 payments a year times 7 years for a total of 84. So if you do this work off to the side, then what you put in here is a little cleaner. So the interest goes here, and the formula is 1 plus the same fraction raised to the number of payments power minus 1. Okay, so remember when we do these, we insert parentheses. One of the biggest things that I want you to make sure is that you have not just looked at what I get in class and just say, oh yeah, that's the answer. Okay, you actually need to actually make sure you can get it on your calculator. Okay, so remember, I'm not going to show you all of these on the calculator, but I'll show you a couple. So remember, we treat a bracket like a parenthesis. So for this one, we actually have 3 open parentheses. 1 for the bracket and then 2 for these that I have. Remember, I put a set of parentheses around the top and the bottom. So it's going to be 1 plus 0.06 divided by 12, close the parentheses for that, raise that to the 84th power, minus 1, close parentheses for the numerator, and then divided by the denominator. Okay, and notice I closed the parentheses for the overall bracket, and then press enter and make sure your answer kind of seems to make sense. So we get $20,814.79 if we round it. Okay. If I asked you to find the interest amount, which I might on the test, okay, you would find the difference between this and how much they contributed, right? And how much they contributed could be found by doing $200 payments times 84, right? So I'll just do that on my calculator and mention it. So you would do 200 times 84, and it's only 16,800 that they actually put in their own money, right? Which means the difference between 20,814 and this would be the interest quantity. Okay. All right, so let's get 22. All right, so 22 is kind of a combo question. It's not kind of a combo question, it is. Okay, so there's 2 different investments going on, and so I want to talk about that real quick. Okay, there's 2 different investments because she has a lump sum of money. Okay, so the 2 different types of investments are, number 1, a lump sum, and number 2 is a periodic payment. Okay, and you cannot figure these together. You have to figure them separately. And so, in other words, we actually need to use 2 formulas. You need to use the compound interest formula for the lump sum, and we're going to use the future value formula. Okay, so this one will be for the lump sum investment, and this one will be for the periodic payment. Okay, so first let's start with the lump sum. So if you read through the problem, they have $200,000 that they're going to roll over. In other words, they're going to move it from one account to the other, and they're going to keep earning interest on it. So we're going to use the formula for compound interest. It's not the PERT one, right? So it's 1 plus R over M to the MT power. Okay, so it's going to be the $200,000, make sure you include enough zeros, and then times 1 plus the interest rate is 7.5%. It's compounded quarterly, and we are figuring that interest for 15 more years. Okay, so notice I did 4 times 15. Technically, if we did it in order, I guess it should be 4 times 15, right? So M is 4 because it's 4 times a year because it's quarterly, and then 15 would be what we get there. So what you end up getting here is actually quite high, $609,659.44. Okay, so I'm not going to circle that because this is only investment number 1. Okay, I still have to find investment number 2, and I have to use the future value formula. Okay, so that formula looks like this, right? We're making, what did we say, $4,000? So $4,000 payments, okay, and then just like the one before it, we need a fraction. So let's figure out what our interest rate is, right? Our interest rate is going to be truly this divided by 4, since it's 7.5%, but then it's getting divided by 4. Okay, N is going to be 4 times a year for 15 more years, or 60. Notice that's exactly what the power is that we used here as well. So we're going to have 0.05 over 4. And then on the top, we will have 1 plus that same fraction raised to the 60th power, and then minus 1. Okay, I'm going to insert these parentheses. And if you punch this in your calculator, you are going to get another $436,970.07. Okay, so I'm just going to kind of circle these. Notice this is how much she has in this account, and this is how much she has because of her lump sum investment. So if we want to know how much total she has, we need to add them. So it would be $609,659.44, and then plus $436,970.07, for a total of $1,000,000. Use your calculator. $46,629.51. Okay, so the point I'm trying to make with a question like 22 is if there are different terms to the investments, if it looks like there's 2 types of investments occurring, you actually need to figure them separately, and then in the end you'll just add them up. Okay, so let's look at number 23. Okay, the Gomez family is in the market to buy a new car. They have a $5,000 down payment, and they have secured a loan with a rate of 11%. Okay, compounded monthly, their payment is $450 a month. Okay, so let's just stop right there. We know the payment. Okay, and we know the cash price of the car, right? So what that means is we actually, we know present value. We actually don't know future value. Future value would be the amount we would pay with interest, right? And we really only know the sticker price of the car. So anytime you see the term cash value or sticker price or anything like that, that means the price before interest. Okay, so notice this amount doesn't include interest yet. So for this one, we use the amortization formula, right? And so let's change this to PMT because that's usually the abbreviation that we use for payment. So if we want to know this, right, we really need to know the present value of the car, and then we'll work back in the down payment in a minute. Okay, so we know the payment, right? So the payment is $450. And then the formula that we use when we know the payment and we want to know the present value looks like this, right? So it is a bracket, as always. And then again, let's write off to the side what we have, right? We have 11% a year, compounded monthly. As far as N goes, we are making monthly payments for 4 years, so we have 48 payments. So this looks like this, right? It's 0.11 over 12. But on the top, it's a little bit shifted around. It's 1 minus 1 plus the same fraction. And then remember, the biggest difference here is we do a negative exponent. So it's not to the 48 power, it's to the negative 48. And then as usual, we need to insert our parentheses. So you're going to punch that in your calculator. So you get $17,411.14. Okay, this is what you'll actually pay. So I'm just going to say you'll pay this in monthly payments. But you have to use some common sense and realize that we also had a down payment, right? So we're trying to find out what the original price of the car was. So we actually have to add the down payment back to this. Because if you think about it, the down payment knocked the price of the car down a bit, right? It actually knocked it down $5,000. So in the end, the actual sticker price of the car was actually, must have been $22,411.14, right? They paid $5,000 right off the bat, which means they financed $17,411.14, and that made a payment of $450. Okay. Okay, so I think we have time for one more on this part 1 video, and then I'm going to switch to a second video. Okay, so in 24, notice it's asking you to find the payment. So we don't know the payment this time. So by the way, you only have 2 formulas where it says payment equals on your formula chart. Okay, and so the real question is, do you know the present value or do you know the future value? Because one of them involves present value and one of them involves future value. So it says what payment is required to pay off a loan of $40,000 over 10 years. Okay, so in other words, you know the present value. Okay, we don't know how much we'll actually pay. We just know we're borrowing $40,000. Okay, so we're going to use the same formula. Well, sort of the same formula as above, right? It's just the twisted version of this one. Okay, so the formula for payment is actually the following. It's, let's figure out our I real quick. So the interest is going to be 10% over 12, right? And then N is going to be monthly for 10 years, so 120. So when we want to know payment, remember it looks like this. It looks like the interest quantity times the present value, which is 40,000, and then over 1 minus parentheses 1 plus that same fraction, but raised to the negative 120 power. Okay, and as usual, we insert parentheses. So I haven't showed you one on the calculator in a bit, so let's look at this one on the calculator. Okay, I'm not going to show you all of them, but open the parentheses for the top, 0.10 divided by 12 times 40,000 divided by parentheses 1 minus, open parentheses again, 1 plus the 0.10 divided by 12, and then raised to the negative 120 power. Okay, don't forget to close your parentheses for the denominator at that point. Okay, so you end up getting, make sure the payment makes sense to you. You shouldn't be getting a payment that seems crazy or unreasonable, right? So in order to pay off a loan of 40 grand in 10 years, you would have to pay $528.60 per month. Okay, notice if I asked you how much interest you would eventually pay, you would find the difference between this payment times 120 and 40,000. Okay.